Well, good afternoon. We're glad everybody's here. I think we're going to have a good lunch and a good presentation today. We'd like to welcome any new members. How many new members do we have? Raise your hand. Yeah, right there, right? Glad you're here. We're glad the students. What class are you from?
Astrobiology, Westminster.
Excellent. Exobiology from Westminster. We love it. Glad you're here. Hope you enjoy this. Just a couple of announcements. We're looking to get our membership dues completed, so if you haven't paid your membership dues, would you get on and get that taken care of? We send a notification out, just a reminder, but if you wouldn't mind getting that taken care of for us. I had to renew mine, hadn't done mine yet, so the reminder was good for me as well to go out there. We're also looking for somebody that would like to help be a web manager for our UGA website. We're going to put some money into that and kind of gussy it up and a few things like that. And we're looking for somebody that would help Paul work on that site for the web manager. So if you got an interest in that, or somebody that would like to do that, we'd appreciate that. The 2019 guidebook's going along well. We're getting articles in, so if you're still working on your article, that's okay. We kind of expect that a little bit. We got people doing multiple articles, so just a reminder to work on that and see if you can get them into us so we can start editing. We're looking like doing the 2-day field trip is the response I've got back. Right now, if we get more response, maybe a 1-day field trip after that, but at least a 2-day right now. And Elliot Jagnevsky is actually, he works for the UGS. He's agreed to be the coordinator for the field trip on that one. So we're going to start working on our field trip, our guidebook for the field trip. We'd like to recognize Rick Ellis as he's here today, former UGS director. He's also going to present in April, isn't it? And stuff that's going on down at the Forge. So we're glad he's here. And also I'd like to introduce Bill Keach. He is the new Utah Geological Survey Director. I'd like to have him come up for just a minute.
I can wait.
No, just tell us who you are. And
Here?
Sure. We're live. We're online.
You're live. That's right. You're sending this. For those that don't know me, my name's Bill Keach. I've been on the job 3 weeks, something like that, trying to fill the big steps of Rick. And he sat down in front of me, and I've been bending his ear for the last 20 minutes trying to figure out stuff I don't know. So he's been really good to help. Background, undergraduate geology from Brigham Young, geophysics from Cornell. Spent a long time in the oil and gas industry. Worked for a software company called Landmark Graphics for 17 years. And I tell people, you know, I'm a seismic guy, which means if you know what an ultrasound is, and think ultrasound down to 30,000 feet over 500 square miles. And that's kind of where my, well, Code beat, I was on the Code project though. That's the 20 seconds. That's 40 kilometers deep. But that was a long time ago in my life. Anyway, spent the last year and a half at Division of Oil and Gas and Geothermal Resources in California. And back here, still teaching my classes at the University of Utah at Brigham Young as an adjunct. So anyway, glad to be here.
Thank you, Bill. That's all we have for announcements. Is there anything else that we need to announce coming up that we're not aware of? Okay. Well, I'm going to turn the time over to Greg. He's going to introduce our speaker, Rebecca, here, and we're excited for this. It's going to be a good presentation. Thank you.
Good afternoon. I want to thank all of you for coming out. Our speaker today is Dr. Rebecca Williams. Dr. Williams received her BA in Physics and Geology in 1995 from Franklin and Marshall College in Lancaster, Pennsylvania. In 2000, she earned her Ph.D. in Planetary Science from Washington University in St. Louis, Missouri. She is a senior scientist at the Planetary Science Institute. The overarching objective of her inner research is to understand the role of water in shaping the surface of Mars through comparison with similar landforms on Earth. Her research builds upon field observations of rivers and alluvial fans, and she has led fieldwork at sites in Utah, California, Australia, and Chile. She has served in the role of principal investigator in 11 NASA-funded projects as a team member with the MOC, MOC, CTX, and Themis Viz cameras on spacecraft orbiting Mars. And I believe she'll walk us through those acronyms I just listed out. She is a participating scientist on the Mars Science Laboratory Curiosity rover. In 2006, she was awarded the NASA Carl Sagan Fellowship for Early Career Researchers. She lives in Wenatchee, Wisconsin, with her husband, Scott, and their 2 daughters. Thank you.
Thank you, Greg, and thank you to the Utah Geological Association for kindly bringing me out here. I really look forward to sharing with you some of the insights that have been learned and applied from fieldwork done here in Utah to our understanding of the fluvial history on Mars. I also want to express my appreciation to the Utah Geological Survey, who has done enormous aid in a variety of capacities over the years. So it's with great pleasure to be here. I also want to thank a number of colleagues. The research that I'll be touching upon here was done in part with a number of colleagues. I thank them all for their correspondence and discussion, but any errors or things that you disagree with are solely my fault. And of course, I want to thank a number of funding agencies that have sponsored this work. There'll be a lot of references in here. If you're interested in any particular aspect of this talk, I welcome feedback. Please contact me. I'd love to extend the dialogue beyond this brief introduction here. And I saw some really exceptional cookies in the back, so if you get a sugar rush and fall asleep briefly, here's a little roadmap of what's going to be covered within this talk. We're going to start with a historical perspective and kind of walk through what we've learned about the history of surface water expression on Mars over the past 2+ decades. This has primarily stemmed from higher resolution images and topography. One of the things we're recognizing is that valley networks are not always negative relief landforms, but some of them, through the processes of erosion, have inverted and can be termed inverted channels. And we've looked at some of those here in Utah. And these inverted channels are really important because they bridge links within the systems and really help us to understand the entire integration of the fluvial system on Mars, which is quite unique. Then we'll talk more specifically about work done here in Utah to field test and validate paleohydrologic reconstruction techniques, and some upcoming work doing rover operations simulations. So Mars, the 4th planet from the sun, is a hyper-arid desert today. Liquid water is not stable at the surface of the planet. In most places on the planet, it doesn't get above freezing. So at Jezero Crater, we actually have a weather station so we can monitor the daily temperature fluctuations, and we see that from day to night, temperature drops can be quite extreme, over 100 degrees dropping. So it's extremely cold. There's also a thin carbon dioxide atmosphere, and the atmospheric pressure is quite low. So altogether, liquid water is not stable. However, we see evidence that lets us know that there used to be rivers coursing across the planets. There were catastrophic floods. We can see places where there are lakes, small seas, and possibly even a northern ocean. So on the right is an artist's rendition of what Mars might have looked like billions of years ago, and it looks strikingly similar to ancient Earth. It really drives a lot of interest in Was there life on Mars? It sure looks like it had habitable conditions. So understanding what ancient Mars was like relative to Earth and why the two planets have diverged so much, why there's been this dramatic climate change from what we think was a warmer, relatively warmer and wetter ancient Mars relative to the hyper-arid desert that we see today. So let's jump back over a century and think about where we've come from. In the early 1900s, scientists looking through telescopes were mapping out Mars. Percival Lowell was one of them. He mapped out dark regions on the planet, and he also drew lines that he called canals. And out of that came notions that there might be Martian civilizations, and these farmers were harvesting water from the poles and transporting it through these canals to equatorial regions to support their farming activities. That really sparked a lot of imagination within the public, and it surely is part of the reason that we began sending spacecraft to Mars. So it must have been with some disappointment when the first flyby mission, Mariner 4, sent back just a handful of images, and what we saw was a thin atmosphere and a cratered surface. Kind of bad fortune, but a lot of the really cool geology that's present on Mars wasn't really captured in these early images. So the emergent view that came after Mariner 4 was that Mars is like the moon, very cratered surface with a thin atmosphere, and it was kind of a disappointing moment. So I'm really thankful that we continued to send spacecraft to continue to look at Mars and discovered not only large shield volcanoes, huge canyon systems like Valles Marineris, the outflow channels, the polar caps, and one of my areas of interest, valley networks. So here's a couple of examples of valley networks seen in Mariner 9 and Viking images. One thing to note here is the planimetric configuration where you have this long trunk channel and these short, stubby, amphitheater-like termination channels. This really drove a lot of debate as to whether you can form these landforms absent precipitation, that is, where the groundwater fed through sapping processes. So one of the early debates was about the role of precipitation in forming valley networks. As a result of the Viking mission, we had complete global coverage of Mars, and we're able to map out these valley network systems. And some early work done by Mike Carr and colleagues mapped out all of the valley networks globally. And here's just a snapshot comparing Washington State and a section of Mars at the same scale. And I like this quote, which is from their paper. Note the enormous difference in drainage densities between the two planets. 2 to 3 orders lower drainage density on Mars than we observe on Earth. And you have huge areas of completely undissected terrains. And characteristically, you have these long trunk channels and very few short tributaries. You have low stream order systems. So it's dramatically different than what we were seeing on Earth. We're going to take a look at a specific example, Naktong-Valles, and we'll return to this over and over so that you can get a good idea of the evolution of our understanding of the fluvial systems. And again, these large sections of completely undissected terrain relative to this one river snaking through the system. But in 1997, that's when everything changed, and beginning with Mars Global Surveyor. And it was like we really got to look at the full geologic diversity present at Mars, and in particular, our understanding of fluvial systems really changed. So I call that the beginning of the golden age of Mars exploration, which we're still in. So you can see the number of orbiters that have been sent since 1997. Here we are today, and an invasion as well on the surface with several robots, including the Curiosity rover, Opportunity and Spirit, and the first one, which was a microwave-sized Pathfinder. The science motivation behind these missions has also changed over the years. And in the beginning, the mantra was to follow the water. But it soon became evident that just documenting where water had been present, how it had interacted with the surface, and how it's reflected in the chemistry, the mineralogy that we observed, wasn't nearly sufficient. Really, the question we were interested in was habitability. Are the conditions or were the conditions ever conducive to microbial life? And so Curiosity has done a lot of work in terms of laying the foundation that, yes, we think ancient Mars at Jezero Crater was certainly habitable, and now the hunt is on, seeking signs for life. So in 2020, there's actually 2 rovers that will be heading to Mars with that very, very difficult mantra of trying to find out and seek for biosignatures. The European Space Agency has a rover that they've just named Rosalind. And Mars 2020, which will be a sample return mission, is also heading there, both looking for signs of life. So let's return and think about valley networks. Let's step back to Viking. And here is the global map that Michael Carr and others put together. All of those red lines are the valley networks, and were superimposed upon a topographic map. And what you see is that they're really concentrated in this band here, the ancient crater terrain. And this is part of the genesis of the idea that a lot of the surface water flow occurred very early in the history of Mars, 3.7 billion years ago or older, on the ancient crater terrain. When we fold in higher resolution images, particularly from the Odyssey Themis camera, as well as topographic information, you see that the spatial distribution of valley networks doesn't really change, but what you're seeing is more individual branches, and the drainage density increased. If we return now to Naktong-Vallis, we can look at this in more detail. On the left is the view from Viking, and then on the right, you can see with the advent of higher resolution image and topography, these are becoming more space-filling dendritic systems. We're now up to a 5th stream order, and it really is a revolution. So you're no longer explaining these large undissected terrains. You're realizing that the short order tributaries just weren't resolvable in the older data. The topography data from the Mars Orbiter Laser Altimeter was also really key to the story, because we were able to realize that gaps in the system were actually lacustrine basins. This is work done by Caleb Fassett and colleagues, and what he recognized is that a lot of these degraded impact craters actually have inlet valleys and outlet valleys that are at the same elevation. So you have a series of breached lakes, and you can now connect formerly isolated valley networks and form a lake chain system. In this case, the Naktong-Scamander-Mamers lake chain system. And it's kind of astonishing to realize that this is a large system. It extends over 4,500 kilometers in length, and it has a catchment that's beginning to be on par with some of the largest continental scale fluvial systems we see on Earth, such as the Mississippi-Missouri River. But there's more to the story. So one of the game-changing events occurred in 2003, where 2 independent research groups published within weeks of each other. It was kind of an exciting time, looking at Mars orbiter camera images, mock images. And one of the places they zeroed in on was Eberswalde crater, where you see this beautiful deltaic complex. One of the most gorgeous places on Mars, in my opinion. You see this beautiful meander with individual scroll bars, and then a cutoff right there. So a lot of the images I'll be showing, illumination is from the left, if that helps you. You can see there's actually a ridge form here, and then a shadow on the right-hand side here. So this was the smoking gun evidence for persistent flow. No longer can you make the case that these fluvial systems were active for very short, brief periods of time, but this requires persistent flow to enable channel migration, as you see in the scroll bars preserved here, and the recognition that you can have fluvial landforms preserved in inverted relief. What's going on here is you had overbank deposits that were largely muddy on either side of the channel deposits, which tend to be sandier and or cemented materials, And wind is a very powerful agent on Mars. It has stripped away all of those fine overbank deposits and left the channel deposits standing in positive relief. With the understanding of inverted channels, it really was a game changer. We had to go back to Mars and map again and think about not just negative relief landforms, but positive relief landforms. And this slide is showing a couple of examples where we see continuity relationships between valley networks that were recognized in the Viking data. And as you move downslope, they transition from negative relief to positive relief. Good, and these continuity relationships help bolster the interpretation that you're indeed looking at inverted channels. On the right is an example from the southern part of Mount Sharp, near where Curiosity's rover is exploring, and you can see negative relief transitioning to a ridge, a topographic relief, in the downslope direction. So how do you form inverted channels? Well, there's basically three mechanisms that can be grouped into sedimentary and volcanic type processes. On the top, you're looking at an grading fluvial system. Over time, you build up a series of overbank and channel deposits, and then wind comes through and strips away those overbank deposits. But you need something that well indurates your channel deposits so that they are more resistant to erosion. And that can occur through cementation, or it can occur through clast armoring, where the channel deposits themselves are pebbles or gravels, and they inhibit wind stripping or erosion, any deflation. Alternatively, you can have volcanic processes where you have lava flows that flow down valleys, fluvial valleys, and subsequent erosion strips away the surrounding terrains, leaving that basaltic cap rock as your inverted channel. And here are several illustrations of field locations of those three mechanisms. Starting on the right, this is on the flanks of the Pine Valley Mountains. You can see this ridge is a lava-capped valley, and it has beautiful exposures with road cuts along Interstate 15. In the center are some cemented inverted channels near Green River, a beautiful sinuous form for those. And then on the left is gravel armored. I'm aware of some examples in the Mojave Desert. I'd love to know of some field locations in Utah. So if you know of anything analogous to this example shown here from the Atacama Desert, these are rounded ridges a few meters high. And what's interesting about them is it's just a monolayer of gravels that is sufficient to inhibit erosion and preserve the landform. So if you walk across them, you often step down into very unconsolidated, sand-rich material, so completely uncemented. I should also mention, I cut for time a whole story of why we think inverted channels on Mars are largely cemented. So if you're interested in that, let me know. So let's return to our global map of the distribution of valley networks. And there's one area, Arabia Terra, that's shown there with a box, that always was kind of strange because it seemed to completely lack valley networks. And the question was, well, what's going on there? Those are, it's the right age terrain, and maybe they just didn't form there, or have they been erased? Why aren't they present? And the answer derives from some mapping that Joel Davis did. In white are the valley networks mapped from the Odyssey data. And here's this area that was a big gap on the previous map. And the dark lines are where we've mapped inverted channels. So those channels are bridging the gap and showing that we were just looking for the wrong type of landform. And once we understood that valley networks have different preservation states, we realized there's not really a gap in our record, just a former gap in our understanding. So we're going to return a final time to Naktong Vallis and look at just to the east of what had previously been mapped. And you see that you can actually extend further back and connect various valley network segments to this system if you include the inverted channel shown here in black. So it's this connective tissue that better allows us to map out the full fluvial system. And this extended the area of the catchment by a third. So now you're looking at quite an enormous watershed analogous to the Congo River. So I think this is really quite extraordinary when you think about where we've come from, just looking at this one little valley network, and then realizing that it's actually integrated into this larger system. It's also important to recognize that our model of fluvial systems on Earth was kind of tainting our view. And on Mars, these systems of rivers and lakes, these chains is very commonplace on Mars. It's telling us that you probably had very flashy systems and eventually had to overfill these basins to integrate the system fully. But overall, you're looking at widespread precipitation over large areas to form these sorts of networks. So inverted channels are clearly an important part of understanding fluvial processes on Mars, and there was a real need to do terrestrial analog research to better understand how we could use them to understand the magnitude and duration of flows on Mars. And so years ago, Tom Chidsey was kind enough to send me this image. This is what started all my work in Utah, and said, you really need to come out here and take a look at this. That particular following year was the GSA meeting. So after that meeting, we went out and met at Ben's Tavern in Green River, had a discussion about going out and looking at these in person. And Brian Curry, who's the gentleman in the lower right, he called these inverted channels the noise in his data. He had done a lot of mapping in the area we were heading to. And I thought, well, I'm interested in the noise in your data. And he said, well, I didn't realize my noise had planetary implications. He was nice enough to join us for a morning and help get us grounded as we started to explore this area. The following day, we actually chartered a plane, and I don't regret a lot of things in my life, but I did have a moment of panic as I realized that many people that I work with, admire, and my own father were on this plane, and the pilot walked up and seemed to have the flight manual, how to fly a plane, in his hands. He also, and I'm not kidding about this, after we got into the aircraft, he duct taped my door. And then right before we took off, he reached over and took his heart medication. So I wasn't sure if this was the greatest use of Smithsonian funds, but you can see our flight path. We spent a lot of time circling around Green River, looking at outcrops, and immediately as we became airborne, I stopped panicking, and the geology completely consumed my mind, because what we were seeing were inverted channels everywhere. So I knew about one location. I didn't realize the Colorado Plateau had so many of them. It was absolutely incredible. One of the first observations that became really key is that you can see a lot of these systems are stacked. You're looking at time transgressive systems, clearly aggradational, so you're building up individual channel deposits over time. And this is really important because we were looking at images of Mars and assuming everything was from a single system, and it began to question the connections that we were making. Here's an example from Mars where you can see clear evidence of this channel stacking. This is again at Eberswalde crater. So this is our main field site. Cedar Mountain Formation, Cretaceous age, channel deposits snaking through here. And this particular area was one that had led us to believe that we were looking at a junction, and the rule of the V suggested paleo flow to the southwest. But once we were airborne, and do keep in mind, this is before Google Earth, okay? So the only way you could really see these things from the air was either via a plane or a satellite. But once we were in the air, you could clearly see there's a topographic step down, and this is an earlier channel deposit. This is a later channel deposit. They're not connected in time. And work done by Ron Harris in the 1980s, looking at paleoflow indicators on the ground. And we saw the same thing, indicated that clearly the flow was to the northeast. So this is a real cautionary tale as we look at Mars and don't have the ground truth, to be careful about your assumptions in mapping these and assuming flow direction. Another lesson that we learned is, again, recognizing paleofluvial deposits and what those landforms can look like. Most of the inverted channels have a rectilinear cross-sectional profile, but there are areas where the caprock has been stripped away and eroded, and you still have what we call a ghost channel. These are not channel deposits. This is stratigraphically below the river. It's what the river was carving into, but it can still preserve aspects of the flow path, so you can still see the area that was where the water flowed, even though you're not looking at the actual fluvial deposits. Here's an example on Mars of the same thing, where you have the caprock, and as you move to the south in the frame, you'll see a more rounded form. So you're getting some of these ghost channels. Another thing that we looked at in detail was connecting the sedimentology to the ridge topography. So we found that point bar deposits were often in lower relief. And then up here, you're looking at sandstone channel deposits that tended to have more rectilinear form. And we hypothesized that this was a better preservation of the channel width, which is an important parameter when you're trying to estimate flow. Another thing about inverted channels that's really extraordinary is they have beautiful 3D exposures of, so that you get multiple different geometries exposed. Here we have a beautiful channel fill deposit. Again, good ground truth to help constrain flow dimensions, particularly width. We made a number of measurements, so I employed Tom Chidsey to measure how high the caprocks were. We also had some GPS survey equipment, so we could do high-resolution topographic profiles to look at like the ridge top slope. We looked for bar cross-set thicknesses to, again, determine how thick the flow was, with flow depths estimated here of just a few meters. And all of this information allowed us to go back and look at various models for how to estimate flow discharge, because we're interested on Mars on how much water was involved and for how long in these systems. And we compared two different types of approaches. One is an empirical form where discharge is related to the planimetric form, whether that's channel width, meander wavelength, or radius of curvature. There's also a physics-based approach which explicitly accounts for gravity, and basically you're looking at using the shield's threshold stress to determine critical velocity and depth. And the inputs here are important. You're looking at channel width, slope, and grain size. When you think about remote sensing, we have these measurements can be well made on Mars with the data sets we have available, but the physics-based approach means that you need to estimate or guess at the slope. Often the ridge surface and inverted channels does not preserve the channel gradient, so it's not a useful measurement to make. And grain size is completely unconstrained, and that can really alter your estimated discharge to the order, within an order of magnitude. So at the Cedar Mountain Formation inverted channels, we had all the data that we could compare and contrast the different models, and it gave us good confidence that we can actually use these empirically derived relationships on Earth that are just based on easily measurable parameters to give us a good, rough first-order estimate of the discharge, and there's no need to go to the added extra uncertainty associated with these unconstrained parameters. If you'd like to read additional information about this field locality, there's a couple publications I'll point you to, and I'll note that the UGA cover is prettier than this GSA cover. But the GSA volume also has another noteworthy publication that you should check out. Utah has a wide range of geology analogs that are really relevant to Mars, from glacial analogs to congregations to dune fields, aeolian processes, and many of these are detailed in a lovely paper by Marjorie Chan and colleagues. So I would be remiss if we didn't spend some time on the ground with Curiosity, our field geologists, and talk about some of the challenges and interesting aspects of using a rover to try to do field geology. This is a beautiful picture at the Buckskin drill target, and you can see the drill site down there at the bottom of the screen. This image is actually taken from the hand lens camera. That camera is meant to get up close to rocks within a centimeter and look at grain size. But since it's mounted on the arm and the focal length is at infinity, it can also take pictures, it can take selfies. So you're actually looking at 59 images that have been stitched together. So those of you that are really observant can see that the arm has been edited out. See, that's and the shadows have changed over the time that they had to manipulate the arm to take all 59 pictures. But every once in a while we get selfies, and I really like them. You can see Mount Sharp in the background of our field site, and it just is really incredible to see our rover on Mars. So Curiosity was sent to Jezero Crater. This is an impact basin that's over 100 miles across. And it's really impressive because it has layered sedimentary rock that forms a mountain over 3 kilometers tall called Mount Sharp, or more formally, Aeolus Mons. The reason that Curiosity was sent to Jezero Crater is because the geomorphology strongly tells you that water was a really important part of the history at Jezero. You see all along the crater rim basin these valley networks that have incised. Some of them have terminal deposits. You have alluvial fans shown here in tan and deltas shown in green. And this map is from work done by Marissa Pelusis. And what she did is she was able to correlate many of these landforms and identify discrete lake levels. These are lakes that postdate the formation of Mount Sharp. So there's been at least 3 lake levels that can be identified by the termination points of valley networks and alignments with features such as the top slope of deltas. The Curiosity landing site was on the plains, the crater floor here at the distal end of the Peace Vallis fan, and so that gave great confidence that we were likely to see water-transported sediments within the landing ellipse. And indeed, we landed on fluvial conglomerates, and early in the mission, there was quite a lot of excitement and interest in the fact that we were seeing riverbed deposits. So here are just a suite of examples that show you the conglomerates that we encountered that dominantly had fine gravel-sized rounded clasts, and those are telltale signs of fluvial abrasion, vigorous abrasion to get that rounded form. Some of the conglomerates we saw had larger clasts. You can see tens of centimeters in that example there. Another famous outcrop is Hada, and this one I selected to show you some of the sedimentary textures that are really key to, again, inferring a fluvial origin to these conglomerates. You'll see aligned pebble beds and tight glass-supported framework. So with observations of the conglomerates, we can look at the grain size distribution shown here on the left and use that to infer flow conditions associated with these conglomerates. Now, we saw no geomorphic expression. We have no idea of the size of the riverbeds. We just saw patchy distributions of conglomerates along course with, in general, a maximum grain size of a few centimeters. We can use physics and the critical Shields number, input slopes in the area, and our observed median grain size to back out depths and velocities of the flow. And you can see that you're looking at flows that are less than a meter, moving at less than a meter per second. And I can see some people are falling asleep, which is why I think it's better to always show your science in graphic novel form, especially if you have Indiana Jones, also known as John Grotzinger, and Laura Croft to tell you about the science. So this is a NASA publication I did not know about until I was reading it to my daughter, true story, at bedtime. So but it's really cool to see that they have a sketch representation of length. That was one of the first conglomerates that we were looking at 2 slides ago, talking about the rounded pebbles within the stream bed deposit, and then discussion of the flow conditions, that you're looking at a speed that was equivalent to a walking pace and ankle deep to hip deep. And that's a much more visually appealing way to present results if I was that artistically gifted. So one of the things that is kind of fun for folks like you to think about is the challenges associated with doing field geology with a rover. And it's something that is still something I wrestle with. The team often worries about whether or not we're missing the good stuff because of how we acquire data, when we acquire data, and the decisions that are made and kind of hardwired into the system. So Eileen Yingst, for a number of years, has been doing field tests of these operational strategies to try to understand the best way to collect data with a rover. And it's quite a mind trip, I have to tell you. So the typical way that you do this, and most of these field tests have occurred here in the state of Utah, I should note. The traditional way of doing rover-based geology is what's known as the linear approach, and it's one way. This is my husband. I've taken him in the field, and this is exactly what he would say. If I see something interesting, we'll stop, otherwise we need to keep moving. And I'm not turning around. So it's definitely a one-way process. In contrast, you can do something more akin to what field geologists do, which is a walkabout. You collect data, and then you walk and you talk about it, you think about it, and then you decide to go back to where you were, often more than once. So it's not a linear process, which is inherent in the field of geology. I just wanted to show you what the data is like that we get, just a snapshot. So this is an example of part of a mosaic. You can see we had 360-degree coverage. That's Mount Sharp, and this is the area down at our feet, and then a blow-up of a section of that mosaic. So on a good day, this is what we have. For Mars 2020, these will be in color, but for curiosity, the first data, and sometimes the only data we have, is black and white images. And then these are footprints for different instruments that you can start thinking about how many image frames you might need to build in a mosaic. For example, that little box is the remote micro imager, the closest that you can get with our remote sensing suite to look at images. So some of the challenges are what observations were planned, what people chose to do when you get that data back, and the timeline when decisions are made, which sometimes occur before the data has returned or when you have very little data. And so this is really different. Many of you who have gone out in the field are used to being able to see everything that's around you, to easily crouch down and get a closer look, to pick up a pebble, to break a rock open with a hammer. These are all luxuries with a rover. So it's definitely a different mindset to approach geology, field geology with a rover. So here are a couple of the recent tests that Eileen has led in 2 locations, near Green River and in the Uinta Basin. And we don't actually take a rover out. We take grad students out with instruments. So they collect the data, they return it to each of the operational teams who are not allowed to visit the field site. They're nearby, but they're receiving the data, making the decisions, and then dispatching the rovers, also known as grad students, to go and take pictures with a camera, either kind of landscape shots or close in like a hand lens. We also had a spectrometer, so they're getting a remote sensing information that's akin to the chem laser. They're learning a little bit about the mineralogy. And if they choose to sample, we also have a field portable XRD, so they're able to get mineralogical information as well. So in brief, I just want to touch on these sites. One of them we dubbed Curiosity Mesa. And there's the scale bar, 10 kilometers. So it's many kilometers field site. And we were looking at quite a bit of section from the Morrison Formation, not up to the Mango Shell, up to part of the Cedar Mountain Formation. And this particular field test was kind of like a needle in a haystack. So the driver here is to look for biosignatures. And there was one layer, I believe it was at the top of the yellow cat member, this cliff-forming layer right here, we nicknamed SWAM, Siliceous Wavy Algal Mat. So there was just one layer within all of this section that has the biosignature. And those of you that are fossil hunters know that finding fossils is often a matter of putting in the time and looking and making sure you're looking in the right environment. In contrast, we went to a place we called Dragon Station in Evacuation Creek, a much smaller field site. But here we had abundant mega biosignatures, like you would trip over them. They were everywhere. They were at your feet. They were an outcrop vertically. I was really worried, I have to tell you, that if we did one of these rover operation tests and they didn't find the biosignatures, we really had a lot to be worried about. So what did we learn? Well, you're not going to be surprised that the team found the Walkabout to be the approach that yielded the best scientific return. It saved time and resources. And a lot of that has to do with the fact that the geologists had time to build up the geologic context, to come back and test and validate their hypotheses for depositional environments. And they were also able to prioritize sites of interest to return to. So Curiosity's most of the mission, we have been operating in the linear mode, but here is one example where we did do a walkabout at a place called Pahrump. And this is an area that's the size of about a football field, so we're not covering a lot of real estate here. But each of these dots are places where the rover stopped. The white dots are the first drive-through, where we took a lot of image data and chem data. On the second pass, the red dots are where we were allowed to pull out the arm and get close-up images. So here is one from the site Mojave, where you can see these beautiful lenticular laths that are interpreted to be pseudomorphs of calcium sulfate. And then in the final pass, we actually drilled at 3 sites, shown here with yellow. Now, this was an extraordinary field campaign, but it comes at a tremendous time cost. This took over 6 months to complete. And so picking and choosing locations where Walkabout is executed is very important. Looking to the future, Mars 2020 is going to be a really impressive rover. It's basically the same body as Curiosity, but we have some different instruments. And yes, the wheels have been upgraded, so they're ready for rugged wear. The mission is a little bit different here. We are collecting samples to return to Earth. So the stakes are really high for any place that you choose to drill. We have 37 total slots for cord samples that ultimately we hope to return to Mars. That mission, the samples back home, the sequel, so to speak, is still in the planning stages. What the working notional hybrid operational scenario is at present is going to be a combination of linear and walkabout. And what's envisioned is that you would take a beeline to areas called regions of interest. Within those regions of interest, you would do campaigns, and those campaigns would be over football-sized field locations where you're allowed to do a walkabout. And you might have 2 or 3 campaigns within a region of interest, but once you leave that region of interest, you're drive, no stopping, no turning around until you reach the second region of interest. So the idea is that a lot of the legwork should be done by really well characterizing the site through mapping, using all of the remote sensing image, topography, and spectral data to best identify those regions of interest. Now, just to appreciate how ambitious the plan is for Mars 2020, we're comparing a prime mission of 1.5 Mars years, and they're anticipating to cover 15 kilometers relative to the 11 kilometers that MSL did and collect 20 drill samples. During that same time period, MSL scooped twice and drilled 6 times. So you can really appreciate that the ticking clock will be always on the mind as we try to collect as many high-quality samples as possible during that period of time. The field location, the field site for Mars 2020 has been announced. It's really an extraordinary site. It's generated a lot of interest in the community, and I, for one, am very excited to see the ground observations from Jezero Crater. It's not too far from Gale, where MSL is located, and within this impact basin, you have a valley network that has breached the canyon wall and a beautiful deltaic deposit. Through mapping that has been done so far, they have identified a number of potential lake levels corresponding to the delta surface, as well as an exit breach. So the lake could have been 100 to 200 meters in depth over its lifetime. And the spectral signature is also really interesting. The deltaic deposits are comprised of clays and carbonates, and then this green band here, I'm really interested in these marginal carbonates. So potentially, we're going to have the opportunity to really explore a near shoreline environment, which is a high biosignature preservation zone. So I think this is really going to be extraordinary when we touch down in 2021. And a lot of the work has already been done to try to sketch out various scenarios. One of the real game changers for Mars 2020 is in the landing system. They're going to be employing terrain relative navigation, which is why this landing ellipse is so small. But they're basically going to be able to pinpoint the landing as it's descending. Descent cameras will identify landmarks and be able to nudge the descent and basically stick the landing and certainly avoid areas that would be more challenging to navigate across. So in this notional traverse, 2 potential landing sites have been identified. You can see several regions of interest have been identified. And they've even gone so far not only to hypothesize about the stratigraphy that we see here from olivine carbonate-bearing floor units all the way up to the inverted channels, but to actually earmark what 17 samples they might want to get. So 3 have been earmarked potentially for delta and lacustrine deposits. Now this is all notional, but it gives you an idea of the level of detail that's going into pre-planning. With MSL, we had a large landing ellipse, 25 kilometers across, and although the team sat down and did geologic mapping, we didn't know where we were going to land, and so it was the first week of the mission where we're finding out where are we in the ellipse, and in fact, the scientists were a little bit rogue and convinced the project to drive away from Mount Sharp, the main destination for the rover, and head to the east to an area, a triple junction of 3 geologic units. We won't be in that scenario for Mars 2020 because of the capabilities of the landing system. You'll have a good idea of where you're going to land, and the landing ellipse is so much smaller. It's really incredible. So we are preparing for, Eileen and crew are preparing for another one of these rover operational tests. About 1.5 years ago, the Utah Geological Survey did an extraordinary workshop where several Mars planetary scientists walked along a shoreline here along the Great Salt Lake and became very humbled about the challenges ahead with trying to do rover operations in the best job possible for searching for biosignatures. And it's much easier when you have someone who knows the answers and can guide you along the way. But when you're the first ones exploring a region and you're doing it with a rover, it's a tremendous hurdle. So I'll leave you with a couple closing thoughts. Over the last 2+ decades, we've really grown to appreciate the history of deposition and erosion on Mars, and in particular associated with fluvial systems, some of which are preserved in inverted relief. There's a lot of evidence for widespread precipitation and runoff. Utah, you folks are lucky to live here. It's a geologic paradise, but it has a lot of important natural laboratories that can be exploited to test both science hypotheses for Mars as well as rover operational approaches. And I think we all have to be mindful about using a rover as a tool and realizing that we're really, despite our best efforts, only doing reconnaissance and skimming the geologic records. We're getting a very incomplete picture. And if you'll indulge me, I just want to show 3 more slides from curiosity, because one of the great joys of participating on the mission is seeing new vistas. So to give you a little context, we've spent the last 1.5 years up here on Vera Rubin Ridge. This is the rover's path. And this is just the lower part of Mount Sharp within Jezero Crater. Ultimately, the rover is planning to, we're right now in the clay unit, but we'll be climbing up this valley and ascending the lowermost flanks there. So exciting times ahead. Some of the pictures we get back from the rover, I think, are really artistic to me. These aeolian bed forms look a lot like brush strokes across the surface. And this image taken 2 weeks ago, there's the top of the Vera Rubin Ridge, and we've just driven past this hill that is comprised of trial cross stratification, leading several people to think that perhaps we have fluvial deposits associated with this little knob. There's a lot of these little remnants that we'll be passing as we continue on our trek in this direction. So I thank you very much for your attention, and I'd be happy to try and answer any questions. So that's a great question. We do know there's liquid water in the North Polar Cap. There's also water that has been confirmed in subsurface ice, both through radar images as well as through rover operations in the higher latitudes through the Phoenix lander. But understanding why the atmosphere changed so dramatically, perhaps there was catastrophic atmospheric loss, and it's possible that some portion of the water inventory was lost to space. Yes.
As far as the scale comparison between the Mars surface and, like the terrain scale and the Cedar Mesa analogs, what were they as far as scale comparison?
Yeah, so the Cedar Mountain Formation inverted channels are about 75 to 100 meters in width, and that's very characteristic of the bulk of the inverted channels that we've mapped out, particularly in Arabia Terra. There are some inverted channels or candidate inverted channels. Sometimes we don't have great geologic context, and so, differentiating interpreted inverted channel relative to other ridge-forming mechanisms can be non-diagnostic. But there are some larger ridge forms that can expand to a couple hundred meters in width. Yes, Marjorie.
What will be the new name of the 2020 rover?
Well, if history is any precedent, there'll probably be a contest that involves students, school-age children. So I don't know, do you have a good candidate name in mind? But I, for one, would like to have a name. I don't like when they put the calendar year associated with missions, particularly early in the planning process, because sometimes launch schedules change, and so it's nice to have a consistent name year after year. So I'm looking forward to them naming Mars 2020 soon. In the back.
Is there any signs of Curiosity slowing down at this point, or is it just kind of chugging along?
Yes. Curiosity is becoming an old rover, and there's degradation certainly to the wheels as well as to some of the instruments. In terms of power generation, we're still doing quite well and exceeding engineers' lifetime expectancy on that. However, it will become further into the mission a limiting factor such that you may not be able to do all of the activities. So at present, all the instruments are healthy, all of them are functional. But yes, there is some wear and tear and some degradation. But overall, the engineers, one of the great things they do is they're extremely cautious and they safeguard that rover from all the crazy ideas that geologists have of climbing up slopes to get a better look around. So overall, we're in good shape. I don't have specifics about lifetimes of various instruments, but we're thankful to be in such a good state.
Yeah, you showed a couple of slides of biomes in sea rock formation. Obviously, you don't expect to see such a thing.
Wouldn't that be wonderful?
Have you seen anything resembling those at all?
Nobody has been brave enough to couch that. One of the real challenges with seeking signs for life is creating an environment where we can debate all of the hypotheses and understand how to interpret candidate biosignatures and differentiate them from non or abiotic processes. So there's a lot of sedimentary structures that can look like pseudo biosignatures, and getting down to the nitty gritty and distinguishing them becomes more and more important when you think about taking a sample and saying this is a sample we need to bring home. So challenging. I welcome the discussion on that. A lot to think about.
So your stacked channels imply accommodation space, subsidence, or some way of changing base level, right? And so, what thoughts do you have in that? And then obviously, then to exhume them, then you've got to do the opposite. You've got to lower your base level. So you're kind of, anytime you see stacked channels, you're seeing a fairly multi-step geologic process. So
Multi-step, long-lived geologic process, absolutely. So many of the inverted channels that we're seeing in Arabia Terra are associated with those inferred lacustrine basins, the degraded craters with the inlet and outlet breaches. And we're actually seeing many of those inverted channels corresponding to individual lake levels. So we do think in some cases, this is not true for all inverted channels, but some of the base level control could be lake level. In terms of exhumation, I think that process is almost always dominantly aeolian. So it's different than here on Earth. We're just not seeing evidence of water stripping the deposits. So I hope that's partially answers your question. Great question about drones and using them. That's certainly that hotbed new technology that folks are deploying everywhere. And we did in the last field test use a drone. How to fold that into rover operations is an interesting exercise because drones collect a lot of data in a short amount of time. You'll be interested to hear that Mars 2020, there is going to be a drone. It's called Mars Copter. And it will be making I didn't make that up. They will be very short flights of 3 to 5 minutes in duration. It will only be operational, as I understand it, on basically a week, once per week. But getting the data back to Earth, I think, is one of the more significant challenges, that and landing safely. It does need to be close enough to the rover to communicate to the rover so that that data can come back. And so one of the other considerations is making sure that the Mars Copter is an asset in that it's always feeding forward to rover operations, as opposed to we need to wait for the copter to fly so that we can drive. If you're driving 100, 200 meters a day, you could move faster than the copter does each week. So they're still working out the sequence of that.
One more question. Adam.
You show in the beginning of your presentation the comparison between Mars and Washington. On that slide, was it
just cut channels.
So if you went back and did a similar study, the amount of Mars drainages would increase in that image?
It would increase. Now, I have to confess to you that I showed you one of the sweet spots on Mars so that it was the most dramatic. And there are still areas where even factoring in higher resolution and considering different preservation states of valley networks, there's still drainage densities that are far lower than we see on Earth. And part of that might be erosion, erasing the record. Part of that might be the role of groundwater in forming some of these systems so they're more sapping derived as opposed to precipitation fed. Just depends on where you're looking, the specifics.
What's the resolution of the imagery across most of Mars?
So we have a huge luxury right now. So Viking, it was about, at the equator, 250 meters per pixel. Odyssey, when we did the next level global survey of valley networks I showed you, that was 100 meter per pixel resolution. The CTX camera now has covered 98% of Mars at 5 meters per pixel. And then we have little postage stamps from, for example, HiRISE and Mach that have better resolution than that. HiRISE gets down to 25 centimeters per pixel. So it's, like I said, we're in the golden age of Mars exploration, and the data is extraordinary. Thank you so much for your attention. It was a real pleasure to be here.
Our speaker gift to Dr. Williams is a UGA publication, Geology of the Utah State Parks. And we want to thank her very much for her coming out today, and also all of you for your attention. Just to announce next month's speaker, it'll be Bob Beek, and he will speak on large slide masses in the Sevier and Martagant Plateau in central Utah. Thank you again.